Yeah. So this is the objective. You have to learn a function from the data space to some space Z such that some downstream tasks such as classification, supervised classification are easier in terms of requiring lesser supervision or being more robust on Z than on X. So this is the goal. Okay. See, we have already seen learning some of these Z's, right? For instance, the latent vectors that we get from the latent space of VAE is one such function that we already have. I mean, this F theta is the encoder of a VAE, PQVAE, for instance. And if you train a DDPM, DDIM, right, the inverted samples are another example, right? But those are the generative way of finding out the Z. In fact, uh, this guy Jan Likun was there in India, right? A couple of weeks before he gave multiple talks. So one of his favorite slides is where he says that, I mean, this is called representation learning, right? I mean, learning a transformation or a projection of data onto some latent space such that the data is represented better is what is called as representation learning. There are two ways to do it. One is the way of generative representation learning, where you build a generative model that involves a latent space like a VAE. The latent space of that generative model itself will become representation for data, right? So that is one way to do it. There's another way to do it, which is the self-supervised learning way. And the self-supervised learning way, no, is not generative. Is that okay? So I'll write that down. So learning representations, learning F theta, which is what I call as representations, can be done in two ways. One is the generative way, where implicitly learn a latent generative model, learn a latent generative model, we have seen this already, right? The example is that you can use the encoder of a VAE as the representation. This is one way to do it. The other way to do it, which we will see now, is the self-supervised learning way. Okay. Self-supervised learning, where the idea is that, see here, what are we doing, right? We are learning, we are learning to sample from the underlying distribution using a latent variable model. Okay. And the latent space, basically what you do here is do a posterior inference, right? Posterior inference is what we are calling as representations, right? So now in self-supervised learning, what is done is define pretext tasks. Okay. Using pseudo labels, and use the representations given by the pretext task solver network. Huh? So what is the idea? The idea is, let's say that you are given some images. Okay, so you build a neural network. Okay, call this as f theta. What this would do is take an image. Okay, and like take its rotation, let's say. Okay. And this network would simply predict the rotation angle. Okay. Train this network to predict the rotation angle and take the penultimate layer of that as your Z. That is what I'm trying to say. This is one of the pretext tasks. The other can be take this, okay, and uh, take noise, okay, and build a network that would classify between this and this, and use the representations of that as you will see. This is classify between noise and data. So what is shown is that if you solve like pseudo tasks like this, these are called the self-supervised tasks. Basically, you're given data, create some pseudo tasks using self-supervision, right? And a network that would solve those self-supervised tasks, they are shown to have properties, right, or representations that are very strong in solving the underlying uh, downstream task, right? I mean, it will learn the underlying distribution is what has been shown. So the question is, I mean, two things. One, why should this work, right? I mean, why should solving these kinds of pseudo tasks should give you good representations of the data? So that is the first question that we will be asking. Okay. The second question that we will be asking is, what are the ways to define some of these pseudo tasks, okay, self-supervised tasks, so that they give you a very good representation. We'll answer both of these questions in the next class. Any questions on this?
So we use the same network to learn, or I mean, for this multiple pretext tasks, or it's a different network?
Yeah, those, I mean, I will discuss all that in the next class, right? I mean, there are multiple ways. I mean, empirically, right? Some people use the same network, some people use different networks, and lot of other things are done. We will discuss all of these. Huh?
Okay, so just one question. So, which of these is preferable? Which of these two methods?
Will, as I said, no, all of these will be answered in the next class. I mean, I just gave you two examples. See, there is the other example is that you construct an
Classify.
input kind of model, take the
Okay.
image, okay, and like just mask it and reconstruct the image back. This is called the masked autoencoding. This is what is used in BERT kind of models, right?
Yeah,
This is,
marked sentence prediction bias. Yeah.
yeah, same thing, right? I mean, that there is the masked autoencoding for image-based models as well. There are these are examples. This is like in paint, in painting, right? Or filling the gaps. There are multiple hundreds of ways of uh, 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 defining pretext tasks. So like different people
Text
have
prediction.
different, they generated in come up with different pretext tasks, and all of them have different performances. JPA is one other way to do it. In fact, what is done in JPA is that they take an image, okay, and they uh, randomly take some parts of the image, okay, and call that as context, and give that as an input to a network, okay, and randomly take some other patches and call that as target. So the task that they solve is, given the context, they want to predict the target. See, the basic idea is the following, right? So if you can fill in the blanks, okay, the only way to fill in the blanks is to understand the underlying semantics. That's all. So that is the whole idea. I mean, there is a very nice mathematically grounded treatment of why all of these should work. This is something called noise contrastive estimation, or NCE. We will see that. Okay, we will see why should these kinds of ideas work in the next class, and there are hundreds of ways to do this. Okay, JEPA is one of the ways to do it. Huh? which we will see in the next class. Okay. Okay, so that's it for today then. We'll resume the next week. Yeah, next week there will be a quiz, and next to next week we'll do a hybrid class. Okay.
Okay, sir. Thank
Okay.
you.
Then, huh? Yeah. So again, once again, happy Diwali to all of you. Yeah. So today should have been a holiday, no? I don't know why they didn't make it a holiday. And okay, huh? Thanks for coming. You might have heard some noise, etc., right, today, because I am also traveling and not sitting in my home office. So yeah, excuse me for that. Okay, huh? See, we'll catch up next week. Bye bye.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Happy Diwali.